What I'll start off with today is talking a little bit more about radiant heat transfer, radiative heat transfer, because I think it's the most mysterious of the three transfer mechanisms. I hope that conduction seems pretty straightforward, the gradual movement of heat through a material by way of its atoms bumping into each other in a sense, or assisted by electrons whizzing through the material and carrying heat long distances. That's conduction. Convection is this movement of heated fluid, either naturally with the help of buoyancy or forced by way of a fan, something stirring the system, blowing the system around. Any questions about conduction or convection, things you want to know about? Okay, heat transfer by radiation is more mysterious, so I'll dwell on it for a little longer. As I do this, before I forget, I've got two little radiant thermometers. So these are just cheapo devices that, when you press the button and aim it at something and let go, it remembers what it was doing. It records a temperature, in this case in Fahrenheit. So it's seeing sort of 80 degrees here and there. The wall, it's seeing 70. My ear, it's seeing 96.8. So just you can try these things. It is able to observe the radiant heat coming off something and give it a temperature. So hopefully they'll wander back to the back of the class by the end, and please bring them back and just drop them here. You don't have to say anything. Okay? So the point is, everything in this room really is emitting thermal radiation. It's observable, not with our eyes, but it's observable by machines, and they can judge temperature then by looking at that glow that's coming off of everything. All right, so far so good? Okay. The details, though, sort of matter, and I want to make sure that they're clear here. The radiant power that is coming off the surface, and power is power like watts. It's energy per second. So in metric units, energy is measured in joules, time is measured in seconds. So joules per second, that's watts. And so the energy coming off of a surface, because of its temperature, depends on these four things. I'll do that again. It depends on how well that surface is able to emit thermal radiation. So its emissivity is the name for this. And that goes from 0 to 1, 0 being hopeless and 1 being really good, ideally good at emitting thermal radiation. There's a constant nature of this Stefan Boltzmann constant. There is the temperature to the fourth power, which is crazy big. It's temperature, again, measured on an absolute scale, where 0 is real 0. So absolute 0, there's no thermal radiation coming off the surface. But as the temperature goes up, the thermal radiation goes up fast. It goes up as the fourth power of temperature. So you double the temperature on this absolute scale, and you increase the thermal radiation by a factor of 16. That's important, as we'll see in a minute. And finally, the surface area, which should come as no big surprise. The bigger the surface emitting the thermal radiation, the more thermal radiation it emits. And it just scales with surface area. Double the surface, you double the thermal radiation. Questions so far? Okay. Emissivity is the one that's the most mysterious, I hope. Emissivity is how well the material is able to emit thermal radiation, and consequently to absorb that same thermal radiation. A black surface is as good as possible, whereas surfaces that are as bad as possible include shiny, transparent, and white. Shiny and white are very closely related. What does it mean to be shiny? A shiny surface is one that takes light that comes in and reflects it the way a mirror does. If the light's coming in at this angle, it goes out at that angle. If it comes in at this angle, it goes out at this angle. It's a geometry problem more than anything else. When you shine light, if this is a question, take a laser pointer or a flashlight and shine it at a mirror, and you'll notice the light has a very specific angle it comes off with, and then you can figure it out pretty easily. So that's shiny. White is different from shiny only in that it reflects all the light. In principle, a perfectly white surface, none of the none of the light stays behind. It all comes back, but it loses its memory of where it came from. So when you shine light on a shiny surface, it comes off at what's known as the specular angle, for this bounce off of a mirror. If you shine light off a white surface, it comes out at a random angle. It's scattered statistically and goes off in all directions. And it's still coming off, but you just can't count on where it goes. Savannah? So Savannah's question is a white car, in fact, why does it still get hot a little bit, right? You're familiar with white cars still getting hot. So this is an interesting question that is right along this path. It's white to your eye, and that is important. We see things only in a certain narrow range of the electromagnetic spectrum that ranges from red at what is in fact the low frequency waves, the ones that are wiggling. Their fluctuations, I'll call it that, are slower than the violet end of the spectrum where the fluctuations are faster. We see that swath of the electromagnetic spectrum. We cannot see infrared light with our eyes. We can feel its effects on us in that it can heat us, but that's all. So when we look at a surface, and I forgot to bring out, request that block that's been out here glowing away, and the device that sees it, we see in the visible spectrum only. And so when we look at something and say it's white, what we're saying is that surface is very capable of taking light that hits it and sending it back, albeit in random directions. You okay with the idea that the light comes off in random directions, and that's distinguishing shiny from white? There are materials that are sort of in between, these semi-metallic paints and stuff, that remember some of the direction but not all. They lose. You can't see them. It doesn't look like a mirror. You don't see exactly what the scenery that was that's reflected off, but you see some memory of it. So it's got a kind of a metallic cast to it, sort of trying to be reflective, but not quite. So there's this whole spectrum of modern paints that are in between shiny and white. But they all send light out. Just instantly transparent just simply lets the light through. So you can't see its thermal energy. You can't see its thermal radiation because it simply just lets light through it. And you see the thermal radiation from what's behind it, not it itself. So those are the three choices, effectively, that do not show you their thermal radiation. Okay, but back to Savannah's question about white. We see something as white only in this narrow spectrum of light, and what that means is if that car were heated up to the temperature at which it would begin to glow with visible thermal radiation, and it would glow very poorly because it's white. That requires a little bit of background. The thermal radiation that a surface emits, not only does its power go up as you make it hotter, according to this law, but the range of frequencies and therefore the spectrum of the glow changes. For objects that are sort of at room temperature, give or take, like we are, the glow peaks deep in the infrared, and it's a swath of the spectrum that's doing the glowing. None of it is visible to our eyes, so we cannot see any of the thermal radiation coming off objects in this room. They're not hot enough. But if they do get hotter, then they start to, the statistical frequencies begin to get faster, higher frequencies. The thermal jiggling of the charged particles that are launching these electromagnetic waves is faster. They're hotter, they're moving faster, they're jiggling faster. Then it sort of should be somewhat intuitive. And by the time you get to about 500 degrees Celsius, give or take, the thermal radiation begins to become significant at the edge of what we can see. First off, the first thing we can see is with our night vision. You know, you have two different kinds of light sensors in your eyes. You have what are known as rods and cones. Different animals have different arrangements of these things, but we happen to have rods and cones. We have a lot of rods on the outside of our peripheral vision. We have mostly cones in the middle of our vision where we want acuity and stuff. What's the difference? The rods are very light sensitive, but they have no color vision. They are especially important to our night vision. So in the dark, when you're walking around in a scene illuminated by moonlight or starlight or almost nothing, and you're trying to see, You may have noticed you have no color vision anymore. Why? Because what's seeing, and also you don't have enormous, you don't have great resolution. You can't see the details as well. You're now looking with your rods. They have no color sensitivity. They actually can see deeper into the infrared than the cones can, and so that's what's cooking. In an illuminated scene like this, you are seeing primarily with the cone cells, which come in 3 different types: red, green, and blue. You see 3 different swaths of the spectrum as 3 different color components. And mixtures of those give you the other colors. So the way in which you see is very interesting. It's a subject I go into in the spring course. But your color vision involves less light-sensitive cells that you have. You have them particularly concentrated in the fovea or macula, the part that you read with, the part that sees detail. I think there are no rods there at all. And so your night vision has this sort of dead spot straight ahead. Is this okay? Or questions about that? So in a darkened room, if you start heating up a surface that is not, the surface that is black, for example, that is very good at emitting thermal radiation in the light that we can see, if you heat it up to 500 degrees Celsius, it'll begin to glow with a colorless glow because your night vision's seeing it. No color sensitivity. A little bit hotter, maybe somewhere in the vicinity of 100 degrees hotter, you begin to notice that it's actually red, deep, deep, deep red, because you're just beginning to enter the range of wavelengths, or frequencies, wavelengths. I should be careful using the words. They're not interchangeable, but they're related. You're beginning to see the portion of the spectrum that touches on the edge of the reds. As it gets hotter, you see increasing, you go from the reds to the oranges, yellows, and the mixture gets richer, and you start to see a broader collection of colors. And by the time you get to about 6,000 degrees Celsius, which is pretty hot, the glow is white. It's the white of the sun. The sun itself is glowing with thermal radiation. That's what you see. That is sunlight. It is thermal radiation from the sun, which is about 6,000 degrees at its surface. You don't see the center of the sun, which is super hot. You're seeing this outer surface known as the photosphere, which is opaque enough that it masks the deep part of the sun from you. And it's about 6,000 Celsius. And its spectrum of thermal radiation peaks in the visible and includes some infrared and some ultraviolet. Some of the ultraviolet doesn't get to us, fortunately. That's the value of having ozone. Remember the ozone hole? Is that familiar to you guys anymore? The concerns about poisoning the ozone hole with chlorinated gas molecules. That was a big deal 20 years ago or 30 years ago, but it's, you kind of can take it for granted. In any case, the spectrum of thermal radiation from the sun is big in the visible, but it also extends out into the infrared, which you cannot see, and the ultraviolet, which you also cannot see. All right? So a white car. So back to a white car. White car takes the portion of the sun's visible spectrum that's visible and does a pretty nice job of just sending it back randomly, random directions. It's not a shiny metal. The ultraviolet, I can't tell you what it does with the ultraviolet offhand, but I know about the infrared. So here's the story with the infrared. You can't see infrared light, and you can't judge colors in the infrared. Okay, colors. I'm not talking about colors like red and white and blue and stuff. I'm talking about how, but the grayscale. You can't judge. If you neglect what we call color and just look between black and white and the grays in between, in the visible you can judge what various forms of gray. Middle gray is half as good at absorbing and emitting light as black. Black is super good at absorbing visible light and in principle at emitting visible light as thermal radiation. White is totally awful at absorbing visible light, thermal radiation, and emitting thermal light radiation. Gray is somewhere halfway in between. Is that okay? In the infrared, that same story holds. But we have no idea with our eyes whether an object is black in the infrared, white in the infrared, or middling gray in the infrared. You can't tell because you can't see it. If you shine it, we can tell what gray we've got in the visible by taking a flashlight. You shine a flashlight at it, oh, it's bright. That must be a pretty light gray, maybe even white. Or, oh, there's nothing there, it's black. You can see with your eyes for what's going on in the visible. In the infrared, you can't, but you can use a machine to do that. And if you took a machine where you shine infrared light on that surface, and you had the machine say, okay, so how much light is coming off? And you would walk around this room, you discover nearly everything in this room is essentially jet black. So in the infrared, which you cannot see, there are very few things that are different from black. They all absorb thermal radiation. They all absorb infrared light almost perfectly, and they emit their own thermal radiation almost perfectly. You okay with the idea that what we see with our eyes in the visible may be different from what we can't see with our eyes in the infrared? I'm thinking another analogy. Well, I won't do another analogy. The only exceptions, only important exceptions to this rule that everything in the infrared, the portion of the infrared that's relevant to the thermal radiation at room temperature, the only exceptions are metals. Metals remain, they're shiny in the visible. Turns out they tend to be shiny in the infrared also. And as a result, they are often very bad at emitting thermal radiation. They're not as bad in the infrared as they are in the visible because they tend to have surface coatings spontaneously. They form spontaneously. For example, aluminum metal never stays pure metal right to the top molecule, the top atoms, when it's exposed to air, because it reacts with air. It forms aluminum oxide. It undergoes that reaction. So any aluminum you ever find that wasn't freshly cut, if you take a piece of aluminum and you shave off the surface, well, okay, now you're exposing metal deep from deep within. That actually does have aluminum right there at the surface, at least for a minute or a second. But any aluminum you find that's been sitting out for any length of time has developed a coating of aluminum oxide. Aluminum oxide is familiar to you as sapphire. And what's a sapphire? It is the gemstone sapphire, and actually the gemstone ruby, same thing. They are both aluminum oxide crystals, slightly contaminated with something interesting. I think ruby has chromium, a little bit of chromium in it, and sapphire has, I don't remember what sapphire's got in it, the blue of sapphire, anyhow. So aluminum oxide is a very interesting material. It's very hard. It's almost, it's close to diamond hard. This is a whole other story. But in any case, aluminum oxide is not very, it absorbs infrared light to some extent. And so aluminum metal is not as shiny in the infrared as it is in the visible. It has an emissivity that is not zero. It's higher than zero. Same with all the other metals. All right, so what's the point of all this long harangue? It means that these gadgets that I'm sending around the room that see thermal radiation and they look, for example, at people, it doesn't matter what you look like. Everybody in this room is essentially identical in the infrared. We all glow beautifully brightly. It's one of these sort of great, we're all equal. We're basically all black in the infrared. Okay? I don't know how to say it more better. Is that okay? That's always thought we'd all look the same. Kumbaya and whatever. Okay. Now I'll ask this question. If you wrap aluminum foil around food, can you still warm it as easily with infrared light? You okay with the question? How many think yes, it's just as easy wrapped as not? How many think no, it's a lot harder? It is no. The aluminum foil, the food itself in the infrared is going to be wonderfully absorbing. Essentially all, anything that's not a conducting material is deeply absorbing in the infrared. And so if you shine infrared light on it, it's going to absorb that infrared light and get nice and hot. Aluminum foil is, although it is not perfect at reflecting infrared light, it's pretty good. And so this is one of the reasons why if you want to keep food warm, wrapping it in aluminum foil is helpful. Not only is it hard to warm the food with infrared light, the food has trouble getting rid of its thermal energy by way of infrared lighting. Aluminum is not good at absorbing it or emitting it. So a potato just sitting out there by itself is basically a hot potato. Is basically a black object radiating away its thermal energy as fast as it possibly can. And when you put aluminum foil around it, you knock down its ability to radiate by probably at least you reduce it to a fifth of what it can do, maybe more. And so it stays hotter longer. Okay? I think that's all I wanted to say about wood stoves. So basic idea of wood stoves, you make the thermal energy inside by converting chemical potential energy into thermal energy, and then you send it out in the room. First you send it through the walls of the wood stove by conduction, and then you send it out into the room by convection up and by radiation out. Convection is pretty seriously directed. It goes up, right? Convection. The hot air rises off the wood stove and instantly off the plumbing, the pipes, the chimney pipes of the wood stove. The heat rises off of those. It's often advantageous to deliberately stir the air in the room with a ceiling fan, forced convection, to try to keep some of that hot air down low where people normally live. As for thermal radiation, as the winter shows up, start to notice it in the things around you that are hot. If you're above something, yeah, you're going to feel convection off of it. If you're over something that's hot, you're going to feel hot air rising off it. But if you're beside it, for example, if you're out in the woods or out in a field with a campfire, if you go over the campfire, basically into the smoke, yeah, you'll feel the heat by way of the heated air coming off it, the convection. But if you stand to the side of it, the only way heat is getting to you in any reasonable amount is by thermal radiation. It's a hot glowing object. The coals that are glowing in there, orange and yellow, that's thermal radiation. And you can block it with your hands and you feel the change. Another example of this situation, when you open the freezer for a midnight snack and you stand in front of it, there is cold air in the freezer that is sort of anti-buoyant. It's going down because it's dense. And it's pouring on the floor, and that might get your toes chilly unless you're wearing your nice fuzzy bedroom slippers. But if you stare at that freezer, it feels cold. I hope you all have this experience. What's happening? You and the freezer are both essentially jet black objects radiating away your thermal energy. You are sending thermal energy at it, and it's sending thermal energy at you. But because it's colder than you by some tens of degrees Celsius, it's radiating a lot less thermal energy than you are. Remember that the thermal radiation goes as the fourth power of absolute temperature? So that freezer is glowing very dimly compared to you. So you're sending lots of thermal energy at it. It's sending much less at you. You're losing the exchange. And so you're losing thermal energy to the freezer, and that's why you feel cold. Okay? Same with the night sky. You go out in the night sky, it is not absolute zero, but the sky, that open sky is very cold. It's complicated what exactly its temperature is. But you're radiating at it, and it's barely radiating back at you. It's a huge loss for you. It actually turns out, you may have been told this and had no idea why it's true, that if you want to stay warm, don't stand under the open sky. Stand under a tree. And you're like, but the tree, you're not touching it. Why does that matter? It's because when you stand under the sky, it's barely sending any thermal radiation at you. You're sending it at it, it's gone. When you stand under the tree, you're still sending thermal radiation at it, but the tree is at the same temperature as the surrounding air. It's actually glowing at a reasonable amount, and it's sending back thermal energy at you, and you can feel the difference. Okay? All right. I'll stop and go on to a different topic, which is water, steam, and ice. So I've talked about thermal energy, how to move it around, and now I'll look at one of the ways in which thermal energy affects the world around us by altering the state of this chemical we know as water. And water is probably, it's got to be the most important single chemical in our world. There are other ones, details that matter, but water is just an amazingly important molecule. And so I'll start with this question, which is that a glass of ice water contains both ice and water. That's sort of the definition of the stuff. After a few minutes of settling, so we get into basically an equilibrium situation, how do the temperatures of the ice and the water compare? Okay, so if you went and measured the temperature of the ice and measured the temperature of the water and compared them, what would you get? Any questions about the question? How many think that the ice would be colder than the water? How many think that the water is colder than the ice? How many think they're at the same temperature? Yeah, it is actually they're at the same temperature. You might think, well, how can they coexist if they have the same temperature? They do, and that's part of the story for today. So some observations. Water has three forms or material phases. So there's a solid, liquid, gas. Those are the phases of most materials. There are a couple of other details in the world of phases, but those are the classics. So ice is common at low temperatures, and up to, if you paid attention to where ice, it's common below 32 Fahrenheit or 0 Celsius. In fact, to an extent, it defines 0 Celsius. The regime in which ice is particularly stable is from 0 on down. Water is common above 32 Fahrenheit, 0 Celsius. So that 0 Celsius is associated with the border between where ice dominates and where water dominates. Steam has many names. Steam can be called steam, or it's the gaseous form of the chemical we know as water. And so you can call it steam, you can call it water vapor. It is incidentally a transparent, it's invisible, it's a transparent material. You cannot see steam. So what you often think of as steam, that is actually this misty stuff, that's actually little water droplets in the air, held in place, prevented from falling fast by what familiar force? Not buoyancy, because water is heavy, dense. What familiar force keeps tiny little water droplets from descending quickly through the air? Viscous drag. Yeah, just like germs and dust particles. Water droplets are the clouds. They're experiencing viscous drag. It's keeping them from coming down here fast. Okay, so that is liquid water droplets. Steam is this invisible gas. You can't see it. And one interesting observation is those three phases can sometimes coexist. You can have a glass of ice water, and it's okay. You could have humid air above a lake. It's okay. That's humid air. That's water in vapor form over a liquid water. It's okay. And we'll see how and why those work out. So I got my 4 questions to go after, and the first one is, how can water and ice coexist in a glass? So the answer, well, part of this is to look at the 3 phases. So ice is a solid, and you learned way long ago that solids are characterized by having a fixed volume. That is, it's very hard to change how much space an ice cube occupies. And the other thing is that the shape is fixed. It's resistant to changing its shape easily. Water is a liquid. It still has a pretty much fixed volume. And it's not perfectly fixed. This is an approximation. I talked at one point way back that liquids are incompressible, meaning you can't change their volume. But that's only approximate. If you push hard on the water in a bottle, you can shrink it a little bit. That's how it develops the outward pressure to fight you, to push back on you as you squeeze it. So anyway, the point is that water is almost incompressible. Steam, or water vapor, whatever you're going to call it, is a gas, and that means that not only can it change shape, but it can change volume. Its volume is not fixed. So ice and water have this special temperature, 32 Fahrenheit, 0 Celsius, and below 32 Fahrenheit, solid ice is the stable phase, which means that if you take that mixture of ice and water and you force its temperature to go below 32 Fahrenheit, 0 Celsius, by sucking the thermal energy out of it, or rather letting thermal energy flow out of it to a colder place. It will all freeze completely. In time, will freeze entirely into solid ice. Above 32 Fahrenheit, liquid water is the stable form, which means that if you take a mixture of ice and water and you let heat flow into it from a hotter object, so that you're forcing its temperature to go up eventually, it will eventually all be liquid water. It's only right at 32 Fahrenheit that the two of them can coexist in what's known as phase equilibrium. So, just for fun and games, let me just show you these things. Mostly it's this illustration. I can make very cold ice, and when you go in the freezer and you pull out an ice cube, it typically is very cold. So there's no limits to how cold you can make ice. So I'm going to make the coldest ice you ever saw. There's ice that was sitting around, minding its own business, thinking nothing was up. And now this is super cold ice. I'll need a volunteer to come up here and touch their tongue to it. You know what'll happen, right? So that's bitter cold ice. There is no liquid water around on this stuff. And there will not be any liquid water around on that until it has warmed up by heat flowing to colder objects all the way to 32 Fahrenheit. Then something special will happen. So observation one is that you can make ice as cold as you like. Just, why do this? Well, because, right? Incidentally, I showed this after class to some people. This is to give away the secret for some of those movies you've seen.
Master, the potion is ready. Drink it now.
Those are little droplets of liquid water. How do they form? The boiling liquid nitrogen in the water is tossing water droplets up and atomizing the water. So there they are, just floating around. Oh, incidentally, they descend because the density of that cold air and water is higher than the density of the surrounding ordinary temperature air. And so this is a failure of buoyancy. They're just too dense and heavy. Down they go. All right. Having done that, so now I'll put I don't know if you can hear it, but it's busy in there. So there is water nearly at room temperature, and here is ice, and I could dip it in there, make it super cold, but I won't even bother. And I'll put it in. So what's happening now is the ice phase is the preferred and stable phase at low temperature. The water is the stable and preferred phase at higher temperature. They're negotiating. They're going back and forth trying to figure out what temperature the two of them should be at. Heat is flowing from the hotter one to the colder one, and as heat flows into the ice cubes, it either warms them up, or once they warm up to 32 Celsius, 0 centigrade, the heat stops warming up the ice and starts melting it. That is, transforming it into liquid water. Do I have a better way of this story written out here? Yes. So two things are happening here simultaneously. And just to tell you this, suppose you start with ice. It's very cold, like right out of liquid nitrogen, and you begin to put heat into it. As you put heat into it, its thermal energy content increases, and not surprising, its temperature goes up. So let's suppose we started with liquid nitrogen temperature ice cubes. For the first period of time, it has nothing to do with it. Liquid water doesn't have anything to do with the story. It's just a material that is solid, having heat delivered to it, and it gets hotter. So it would be like putting heat into a block of stone. It gets hotter. Once the temperature gets to 32 Fahrenheit, 0 Celsius, temperature of that ice cube, then something new happens. Additional heat added to that piece of ice no longer makes it hotter. Instead, the heat begins to transform the solid ice into liquid water. The mass associated with solid ice diminishes, the mass associated with liquid water increases, possibly from 0 and starts to increase. Okay, so the heat is doing a different thing. It's not increasing the thermal energy content of the ice. It's increasing its chemical potential energy by turning it into a different phase of matter, liquid. Is that okay? The idea that heat can do one of two different things: increase temperature or melt a solid into a liquid. So, the ice, if you just took a piece of ice and added heat, I don't know, if you hold a blow dryer on it, it'll warm up to 32 Fahrenheit. It'll then sit at 42 Fahrenheit as it melts into liquid water. And only when it's all water will its temperature begin to rise again. So it has this brief period where the temperature is stabilized by the melting process. So you can melt ice into water by adding heat. Oddly enough, you can also melt ice into water in certain circumstances by squeezing it. And this has to do with the bizarre behavior of water. That water is one of the only materials in existence that where the solid form of water is less dense than the liquid form at the same temperature. That is, really cold water is quite dense. Water that's almost freezing is very dense. It's more dense than ice. That is really unusual. What would be a normal thing? Solid lead and liquid lead. I don't know, I just picked them because they picked them. Solid lead is more dense than liquid lead at the same temperature. So basically, solid lead being more dense than liquid lead, solid lead sinks in liquid lead. Solid salt sinks in liquid salt. Solid oil, salad oil, sinks in liquid salad oil. Nearly all solids sink in their own liquids. Is it okay? Ice doesn't. Ice floats in its own liquid. That's why you have icebergs. That is why when lakes freeze, they freeze with ice on the top, not on the bottom. If this weren't true, lakes would freeze all the way through and kill all the animals in the lake. So the fact that ice floats on liquid water is like essential to life. All right? Having said that, what's the point? The fact that if you take ice and squeeze it, the squeezing process is trying to increase the density of the chemical water. And it prefers then to become liquid, which is naturally more dense. So squeezing ice has this strange ability to melt it. Most other materials, essentially all the other materials, you squeeze the liquid, you can turn it into a solid with pressure. Well, ice is the anomaly. Okay, but the main point here is that adding heat to ice first raises its temperature until it gets to 32 Fahrenheit, and then doesn't raise its temperature anymore. It melts the ice. How about water? If you take liquid water and begin removing heat from it by exposing it to a cold place, heat flows out of the water, and its temperature drops until it reaches 32 Fahrenheit again, at which point it begins to undergo a phase transformation into solid. It freezes. So, heating ice up increases its temperature. At 32, it melts it. Cooling water down cools it, lowers its temperature. At 32 Fahrenheit, it freezes it. And so when I put these two, ice and water, together, they fought over temperature until, at this point, there's ice and water both here coexisting. They have reached phase equilibrium at 32. It's a spontaneous, stabilized thing. If the temperature were to go higher than 32, the ice would begin to melt to form water. And that process requires some thermal energy. It will consume thermal energy. So it's hard for that transformation to occur. I'll talk about that in a second. If the temperature were below 32, liquid water would begin freezing into solid water and release thermal energy and warm the stuff back up to 32. So it's stabilized. It's spontaneously stabilized. That energy it's stabilized by an energy that's required to melt ice. That energy is known as latent heat of melting. And the reason that the temperature of ice stops increasing when you hit 32 from the bottom, when the temperature of the ice rises up and reaches 32, adding thermal energy does not increase the temperature. Where's that thermal energy going? It's going into melting the ice, paying a latent heat, it's called, paying an energy bill that's associated with that phase transformation. And it's called the latent heat of melting. The official name is the latent heat of fusion, but I find that name very unenlightening. So latent heat of melting. And this mixture of ice and water can't get hotter, can't get colder without issues relating to that latent heat of melting. If you add heat to it, it's going to go into the latent heat of melting the ice and making more liquid water. If you take heat out of this, it's going to come from the latent heat of freezing water into ice. The energy comes back out on the freezing process. When you freeze water, you receive the latent heat of melting back. It's paid back. Questions about why this stabilizes at 32 Fahrenheit, 0 Celsius? Spontaneous. Doesn't matter how much water and ice there are. If both of them are present and it's well mixed, it's going to be at 32 Fahrenheit. So every glass of ice water you've seen, it doesn't have other things in it, like sugar or salt, which mess up the balance a little bit. If it's pure water and pure ice, man, it's going to be at 32 Fahrenheit, 0 Celsius, whether there's a little bit of ice or it's almost all ice. A little bit about the story of what's happening even now at the surface of the ice, where the ice and the water touch. That surface is not static. Even though, let's suppose there's no heat going in or out of the entire beaker, it's just sitting there. You might think it's completely static, nothing's going on. Not so. There is a perpetual exchange of molecules from the water to the ice and from the ice to the water. And the way I think of this is like the ice is the surface of an airport landing area, landing takeoff. So the ice is the solid, it's the ground. And there are lots of planes on the ground that are part of the ice, basically. And then in the air, those are the molecules that the airplanes that are up in the air, those are the ones that are like in liquid water. They're flying around, traveling through the liquid. There's always a landing and leaving process going on the whole time in leaving the analogy, going back to this. If you look at the surface of an ice cube, there are water molecules leaving the ice cube, like planes taking off, leaving the ice cube for the liquid water, and there are water molecules landing from the liquid water on the ice cube. Landing, leaving, all the time. And at present, assuming there's no heat going in or out of that beaker, the landing and leaving processes match perfectly. A zillion and 8 water molecules land each second, and a zillion and 8 take off each second. So there's no overall change. There really is an exchange of molecules, and it is demonstrable, but there's no net effect. When you start putting heat into this, when you add heat, you cause more molecules to take off from the ice into the liquid water. And the ice shrinks, and the liquid grows. And when you suck heat out of that mixture, you cause more molecules to land than take off. Once they land, you suck the energy out of them, they can't take off again, and you cause the ice to grow and the water to shrink. Okay? So that's the situation for ice and water. They can coexist at one special temperature at which the landing and leaving processes can match nicely. Below that temperature, the landing and leaving processes will not match. If you go colder, it becomes harder for a water molecule to leave the ice. It has to find thermal energy to break free. And at lower temperatures, there's not enough thermal energy around. They break free too rarely. So the taking off process, the leaving process for water molecules from the ice is too slow. And the landing process wins, dominates. And the water gradually lands and becomes ice. And the ice grows until there's no water left. So that's why at below 32 Fahrenheit, liquid water is unstable. The molecules just keep landing relentlessly until there's just nothing left in the way of liquid water. Above 32, the leaving process, it's too easy for a water molecule on the ice to find the thermal energy it needs to break free. Too many of them leave too fast. They can't be replaced by the liquid water. And so the solid ice gradually diminishes as it loses its molecules to the water. They fly off. Fly away, little bird. Off you go. Okay? I did this already. Okay, so it's a seemingly unrelated question, and I talked about this bits and pieces earlier. What fraction of the molecules in the room air right now are water molecules? 6 choices. 5 choices, I can't count. How many think 0%? How many think about 0.2% of the molecules? How about 2% of the molecules? How about 20%? How about 50%? Okay, we're peaking at 20%. It's actually about 2%, give or take. There's no reason you would know except that, well, there are ways of sort of guessing. But the point is that you all learn, and I do think I've said this before, you all learn that the atmosphere is 79% nitrogen, 19% or something like that, or 20% oxygen, and then a smattering of other things, and that adds up to 100. There's a little asterisk on that, and it says dry air. So this is air where there's no humidity, assuming that just leave the water molecules out. The fraction of the water molecules are very dependent on the situation, and they vary with what's known as relative humidity. And associated with relative humidity is also the temperature of the air. And those go together, temperature and relative humidity. And so we got to sort of figure that out. And the point of this, where we'll go, and I'm not going to, I'll stop soon, is that just as there is an exchange of water molecules between ice and liquid water and ice all the time, and it leads to interesting behaviors with temperature, there is also an exchange of water molecules between liquid water and gaseous water, which, if it were pure, there were no atmosphere here, then you would be fair to call it steam, or, because it's a pure chemical. In fact, we've got air here, so the water molecules that come off the liquid and become gaseous water molecules have to share the space with ordinary air. So it's a little more complicated, but not terribly. The point being that there's that exchange of liquid water molecules for gaseous water molecules and back. It's going on all the time too. And right now, there is a coexistence of liquid water and gaseous water. They're coexisting. And oddly enough, that coexistence can occur over a vast range of temperatures. It's not like ice and water, where they can only coexist at one temperature. Liquid water and gaseous water can coexist essentially at any temperature, as long as the liquid can exist. But there are consequences to changing the temperature. At low temperatures, that coexistence occurs when there are not very many water molecules in the gas phase. At high temperatures, that coexistence occurs when there are lots of water molecules in the gas phase. And so what I'll do is we'll look at the role temperature plays in striking balances between liquid water and gaseous water. And the transformations, incidentally, the transformation of liquid water to gaseous water you know as evaporation. And the transformation of gaseous water to liquid water you know as condensation. So that's a job for Friday.